So what I'm going to talk about in the next 30 or so minutes before lunch is I want to talk about energy and electricity. Also, as was mentioned, I'm going to be the one half of the folks talking to the governor on Thursday. So if you have anything you'd like me to mention or think I should mention, come see me over lunch, and I'm happy to note it down and then make an executive decision as to whether I'm going to talk about it or not. But if we're going to think about the impacts of extreme events from climate change, or climate change more broadly on California's energy system, I think it's nice to organize your thoughts in a way that I could explain to my 3-year-old. We're learning the elements so far. So if you're thinking about California's energy system, a very large state consuming a lot of energy across many different sectors, the three angles from which the system will be put under additional pressure is, I think, most importantly, fires and heat, and to a certain degree floods. So I'm just going to go through and talk about how these different impacts from climate change will affect the system. If we break this down a little bit further, which specific angles here will affect which aspects of the energy system here, I think the most important ones here are fires and heat that will affect transmission, then heat and floods, which will affect, or sea level rise, which will affect generation, and then mostly heat, which will affect demand, meaning how much electricity individuals and firms in the state are going to want to extract from the system. To not hold you hostage with the takeaway message here, it's demand that's going to be the big one here, but I want to talk about the importance of the other parts here too, because they're especially related to extreme events. So I don't have a lot of text. I have a lot of pictures that I've stolen from different people. I've now noted that I didn't put sources anywhere. I'm not claiming this material as my own. Again, I'm representing lots of folks who were mentioned on the title slide here. So if we're thinking about fire risk, on the left here we have a map of current day fire probability overlaid on a map of California's transmission lines. These are current day transmission lines. This does not involve what we're planning to do in order to increase the share of renewables from all sorts of places in the state here. And if you're looking at this graph on the left here, there's a tremendous intersection between areas of high or significant fire risk and where these transmission lines run. So if you're looking at the slide on those squares there on the right here, what you'll see is the probability that a given transmission line will be affected by a fire within a 30-year period centered around the year 2085. So this is a pretty interesting map here. Red is bad. Green doesn't mean good. Green just means lower fire risk. But the point here is that these are two different models, because there was some mention earlier about uncertainty from different models. The predictions here are pretty significant. But what you're seeing here, the fire risk is quite high. I think more importantly than just saying that the fire risk is high is thinking about the change in fire risk for these transmission lines right here. And what you're seeing here for 3 different climate models, so top to bottom are 3 different climate models, left to right are 2 different scenarios of climate change. For the B1 scenario is the happy green world, low emission scenario. The A2 is the still, I think, at this day, optimistic scenario, but one of the IPCC's worst case scenarios that we're going to go towards. And what you're seeing here is there's a significant increase in the probability that transmission lines will be affected by fire. And if you look at some here a little bit more closely, let's zoom in on the top right here. What you're seeing here is that, for example, that line to the north, the engineers and power managers in the room know what that line is called, but we're getting a lot of our power up there. So a lot of the lines where we're getting power from up north and also power from the eastern neighbors here may be experienced or are expected to experience higher fire risk. Does this mean, just to make sure we're characterizing this properly, that this picture means a transmission line will burn and fail? No. What this picture means is that these transmission lines will be affected or near areas that will experience increased probability of burning. So this could be ash deposits on the line, this could be just higher temperatures, which makes these lines less effective, or in a worst case scenario, an actual fire to the line. But the two takeaway messages here are existing infrastructure will be affected, and if we overlay our planned infrastructure here, this is clearly going to have a significant impact here. Now, I just briefly want to talk about the effects of heat on power generation and allude to transmission losses here, but what you see here is a picture from a very nice 85-page report that Larry Dale, who's sitting in the back, and colleagues have authored, trying to take a sort of universal look at the impacts of climate change on energy infrastructure in California. And what we're seeing here is the impacts of increased heat on the efficiency of natural gas power plants. So combined cycle and traditional natural gas power plants. During hot days, if you've ever visited one of these places, and the folks who operate these plants notice you're working on climate change, the first thing they'll tell you is during hot days, the efficiency of these plants goes down for engineering reasons that I don't understand. I'm an economist, so I'm happy to point you to the right folks there. So there are engineering relationships which show you how efficient natural gas plants are during hot days. What this study did is it linked a climate model to coefficients that show you how big this effect is at the power plant level, and the panels to the very right here show you the impact on generation for combined cycle and traditional plants at the bottom. The exact numbers here, just to give us an order of magnitude right here, in terms of peak supply loss during extreme heat days, we're talking about somewhere around 4%, I think is the right number. This is a number, but it's not the numbers I'm about to show you when we're going to talk about demand. So transmission lines also become less efficient during extreme heat days or during warmer days, so we get some loss in transmission as well, which that number, according to this study, is about a 1% to 2% decrease in transmission efficiency. Now, I'm an economist, so I love the word demand or consumption. If we're thinking about electricity load, this is the number of electrons pulsating through California's transmission system in any given hour here, and we're correlating this with temperature. What you're getting is a highly nonlinear relationship between temperature, which is on the x-axis here, and the number of electrons or the amount of energy pulsating through the system right here. What you're seeing at the bottom left here, and I'll show you a big version of this picture in a second, is the relationship between temperature and load for the California Independent System Operator. It's a highly nonlinear relationship where at low temperatures, if it gets warmer, the few households in California that actually heat with electricity turn off their heaters and electricity goes down. Also, the blowers that use electric motors to blow hot air through your buildings turn off these fans, so electricity goes down. But as it gets warmer, what do people do? I live in San Francisco, I don't have an air conditioner, but for those of you who live in areas with air conditioners, you turn on your air conditioners at high temperatures. The point I'm trying to make here is we could think of this as an all-California problem, but there's actually quite a bit of heterogeneity in response, right? If you live in El Centro, you have an air conditioner. If you live in San Francisco on the other side of the hill, you don't have an air conditioner. So the point here is how people respond to increases in temperature is going to depend on behavior and the type of capital they currently have in their homes, air conditioners or not. So I just threw up a couple here. I did this grid by grid for your information, just to show you that there's quite a bit of heterogeneity in temperature response across, let's call them subgrids right here. This is the overall California, we could call it the sort of representative response function here, and that's what I want to keep in mind here, is if you have a 3-hour period that is in the 80-degree range, you're roughly seeing a 25% increase in load relative to what you have at a 60 to 65-degree hour. Now, why does this matter? So we have an agreement with California's investor-owned utilities, where we get access to household billing data for electricity. I don't know who you are. Do not worry. Your household is anonymous to me or a number. All I know about you is how much electricity you consumed, how much you paid for it, and the 5-digit zip code. There is no way I can guess who you are. But what we did is we matched these household billing data to temperature data and estimated these responses of residential homes to temperature using actually observed data. So there's no assumptions about your behavior in there. There's not, I think you turn on an air conditioner in San Francisco or not in here. I'm using actually observed data to extract a relationship here. We're then going to use these relationships, and that's what you see here, and match those to projections of temperature and showing what happens to household consumption under different scenarios of climate change. What I'm showing you here is the A2 scenario, which is the scenario we're currently on track towards meeting. And what you're seeing here is that within California, there's quite a bit of heterogeneity in terms of what we expect to happen to increases in household consumption of electricity, with most of the increases here being concentrated in the Central Valley and the southeastern parts of the state. The important thing to note here is we're holding incomes constant, we're holding population constant, we're holding who has air conditioners and not constant, and we're also holding constant the California Energy Commission's efforts to improve the efficiency of both homes and appliances here. And I will speak to that in a second. The point I'm trying to make here is if we hold all of that constant, we're expecting about a 50% increase in residential electricity consumption by end of century, which is a significant increase. Now, I apologize for this rather sciencey, not pretty map graph, but what I want you to think about here is the story I just told you is one where I'm walking along this curve, for example, Cal ISO or anything like that. So during cold days, it gets warmer, electricity consumption drops, and then you go up. So that's one way of thinking about climate change. The way I think we should be thinking about climate change is if you lived through a couple of very hot summers in San Francisco where you had 5, 10, 15 days where it's 95 degrees, what are you going to do if you have a good paycheck? Buy an air conditioner, right? If your landlord will let you put one in, you're going to buy that air conditioner, or if you're building a new home, you'll put one in because you know it'll get warmer. So what happens to this response curve? Well, it shifts up during high degree days because now more people have air conditioners than before. So at high temperature days, that response is steeper, and you're going to walk up the red curve instead of the blue curve. That was not in these previous projections. So a recent project that Guido and his team have funded here is trying to get at that impact of this response. And what we're doing is we're looking at temperature response at the zip code level. So this is not yet official, but I figure I'd show you some new work here. What you're seeing here is the highest, the temperature response at the highest temperature bins that households experience across the state. What I'm interested in are households that live in warmer climates. Do they have a stronger response to hot days than households that live in cooler climates? Do richer households have a stronger response to hot days than poorer households? So what we did is, and here's what I would yell at a graduate student for, a messy table, but the point I'm trying to make here is if we regress households' temperature response on a bunch of characteristics of zip codes, the two things that come out significant over and over again are incomes and climate. Households or areas that are wealthier and areas that are warmer, have hotter summers on average, have a much steeper temperature response than poorer households living in cooler climates. Why does this matter? Again, I'm very much interested in looking at actually observed data instead of making assumptions about how I think people behave. If we're taking a response curve for the residential sector here, and this is just an approximation, and showing what happens to this curve as climate, meaning the average long-run climate you live in, the long-run summer you live in by end of century gets warmer, that response function becomes much steeper. This is not a sketch. This is actually estimated data right here. And at the high bin, that's a 20% increase in slope, which is economically and statistically significant. So that's demand right here. But just to put this in perspective, this matches some of the figures you see in the other studies that have been written about this. But to think about this is by end of century is that the demand for almost all summer days is expected to exceed the current 90th percentile per capita peak load. So the whole summer will look like what sort of 10 days in the 10 worst days have looked like in a given summer. So incredible increases in demand. I'll briefly talk about inundation risk and floods. Lots of power plants in the state of California. I've visited or had the privilege of visiting a couple, and I've learned a lot. I now have several hard hats, which my toddler really enjoys. But the point I'm trying to make here, we have power plants all over the state. We don't have any coal-fired power plants. I also can't stop myself from making the point that that does not mean we're not consuming electricity made by burning coal. We're importing lots of electricity from our neighbors who have large-scale coal-fired power plants, but there are no coal-fired power plants in the state of California. And if you're thinking about a 100-year flood event on top of 1.4 meter sea level rise, which is within the range of prediction by the IPCC by end of century right here, there's a nice map in that report that shows you which power plants are actually at risk from sea level rise. This, again, just to be very careful here, is not saying that these power plants will be flooded and turned off and we will lose all this capacity. This just means that there are some power plants that have been identified that are likely to be affected by sea level rise and storm surge. If we're thinking about substations that are potentially at risk, this is just for the Bay Area. This is a very large number of sizable substations right here. Yeah, let me make this point quickly here towards the end. The important thing to note here is, while it's nice to tell this story that all this power plant capacity is at risk, I think just taking a statistical approach to this is the wrong way to go. So the folks at LBNL who wrote the study actually went out and visited several power plants to check out whether the power plants are actually where the GIS says they are, whether they're actually at the level of elevation you think. We often don't have the resolution we need in order to make determinations here. So if you're actually 1.5 meters higher than the GIS system says you are, that makes a tremendous amount of difference as to whether you're going to be affected by this. It also will determine what measures you can take, preventative measures, in order to protect your particular plant from these storm surge events. So there's a lot more work needed on this, but I think this was a really good first stab at identifying infrastructure that is, again, potentially at risk here. We're talking storm surges 100 years out, or well, I guess now 90 years out. Time flies. I'm going to skip this one here. So the thing I want to have you walk away with here is our best understanding currently is that extreme events from climate change and climate change itself is likely going to have the biggest effect on demand, right? People are going to start cooling. Many manufacturing processes require cooling, so demand will increase mostly from cooling. We're going to have to do a lot of thinking about preparing for extreme events, not just heat, but fires and floods when we're thinking about installing additional infrastructure and how we protect our existing infrastructure from such risks. And also keep in the back of our minds at the same time that climate change isn't the only challenge facing California's energy system. If you're thinking about the impact of population growth on increases in demand in California, that puts a significantly larger pressure on overall electricity demand than climate change does. So uncertainty as to whether we're going to have 50, 60, 70, 80 million people by the end of century in the state versus what climate change is going to do, I think has to be kept in mind that there's a huge population pressure. I'm going to stop right here and leave some time for questions. I know we're already beyond lunchtime, but I'm happy to take questions. Yes? Thank you.